Bismillah, welcome to Think Math. In the previous lesson, we defined the derivative of a function at a point using limits. We saw that f prime of x measures the instantaneous rate of change and the slope of the tangent at a point. In this lesson, we go one step further. We want to answer four practical questions. What is the derivative of f of x itself? What happens when we take the derivative of the sum or difference of two functions? How do we differentiate a product of functions? And finally, how we differentiate a quotient of functions. To keep our work anchored, remember the basic definition. F prime of x equals limit as h approaches 0 of f of x plus h minus f of x all divided by h. All the rules we will see are shortcuts that follow from this definition, but they make calculations much faster. We start with the simplest functions. If c is a real number and f of x equals c, then the graph is a horizontal line. The slope of a horizontal line is 0 everywhere. So the derivative is f prime of x equals 0 for all x. Next, if f of x equals ax plus b is a linear function, the graph is a straight line with a constant slope a. That means the derivative is f prime of x equals a at every point. These two facts, constants differentiate to 0 and linear functions have constant derivative, are the building blocks for all of our later rules. Before we go further, we need one more basic rule, the power rule. This rule tells us how to differentiate functions of the form x to the power of n. For any real number n, as long as the function is differentiable, the derivative of x to the power of n is d by dx of x to the power of n equals n times x to the power of n minus 1. So we bring down the exponent as the coefficient and we subtract 1 from the exponent. Let's see a few simple examples. If f of x equals x squared, then f prime of x equals 2x. If g of x equals x to the power of 5, then g prime of x equals 5x to the power of 4. If h of x equals x to the power of 3, then h prime of x equals 3x squared. The same idea works when there is a constant in front. If f of x equals kx to the power of n, then f prime of x equals k times n x to the power of n minus 1. For example, f of x equals 2x to the power of 8 gives f prime of x equals 2 times 8 x to the power of 7 equals 16 x to the power of 7. And this also means that whenever we have a constant multiplied by a function, then we take the constant out and multiply it by the derivative. Now we look at the sum and difference of functions. Then the derivative of the sum is simply the sum of the derivatives. D by dx of f of x plus g of x equals f prime of x plus g prime of x. Similarly, the derivative of the difference is the difference of the derivatives. D by dx of f of x minus g of x equals f prime of x minus g prime of x. Intuitively, if both functions are changing smoothly, their combined rate of change is just the combined effect of each one. This rule lets us differentiate complicated expressions term by term. Let's apply the sum rule in a simple example. We have y equals 2x to the power of 8 plus 3x to the power of 5 minus 4x plus 6. We differentiate each term separately. The derivative of 2 times x to the power of 8 is 16x to the power of 7. The derivative of 3x to the power of 5 is 15x to the power of 4. We dropped the 5 as a coefficient, multiplied it by the 3, and then the new exponent is 4. The derivative of negative 4x is negative 4, and the derivative of the constant 6 is 0. Putting these together, using the sum and difference rule, we get y prime equals 16x to the power of 7 plus 15x to the power of 4 minus 4. This example shows how powerful and easy the sum rule is for polynomials. We just differentiate each term and add the results. Next, we study the product rule. If y equals f of x times g of x, and both f and g are differentiable, then the derivative is d by dx of f of x times g of x equals f prime of x times g of x plus f of x times g prime of x. In words, derivative of the first times the second plus the first times derivative of the second. This rule is essential whenever we see factors multiplied together. Let's take the example y equals bracket x squared plus 3 close the bracket multiplied by bracket 2x to the power of 3 minus 5 close bracket. Here we choose f of x equals x squared plus 2 and g of x equals 2x cubed minus 5. Then f prime of x equals 2x and g prime of x equals 6x squared. Applying the product rule, y prime equals f prime of x g of x plus f of x times g prime of x gives us 2x multiplied by 2x cubed minus 5 plus x squared plus 3 multiplied by 6x squared. Now expand each part. The first term expands to 4x to the power of 4 minus 10x, and the second term expands to 6x to the power of 4 plus 18x squared. Adding gives us y prime equals 4x to the power of 4 minus 10x plus 6x to the power of 4 plus 18x squared, and collecting like terms we get 10x to the power of 4 plus 18x squared minus 10x. So the product rule lets us differentiate this expression systematically without expanding the original product first. Finally, we consider quotients. If y equals f of x divided by g of x and both functions are differentiable and g of x is not equal to 0, then the quotient rule says d by dx of f of x over g of x equals f prime of x times g of x minus f of x times g prime of x, all divided by g of x squared. A good way to remember this is derivative of the numerator times the denominator minus the numerator times derivative of the denominator, all divided by the square of the denominator. For example, y equals 3x minus 5 over 2x plus 5. We take f of x equals 3x minus 5 and g of x equals 2x plus 5. Then f prime of x equals 3 and g prime of x equals 2. Using the quotient rule, we have y prime equals 3 multiplied by 2x plus 5 minus 3x minus 5 multiplied by 2, all over 2x plus 5 squared. Now simplify the numerator. 3 times 2x plus 5 equals 6x plus 15, and 3x minus 5 multiplied by 2 equals 6x minus 10. So the numerator becomes 6x plus 15 minus bracket 6x minus 10, or 6x plus 15 minus 6x plus 10, all equals 25. Therefore, y prime equals 25 divided by 2x plus 5 squared. This is a neat example showing how the quotient rule combines the derivative of the numerator and denominator. Now let's take more examples for practice. If f of x equals x cubed plus 6x squared minus 36x plus 4, and we want to evaluate f prime of 1 and f prime of 0, then we differentiate and get f prime of x equals 2x squared plus 12x minus 36. Then f prime of 1, we substitute first derivative, we substitute x by 1, so we get 3 plus 12 minus 36 equals negative 21. And f prime of 0 becomes 0 plus 0 minus 36, or negative 36. We want also to find the value of x which makes f prime of x equal to 0. So we set 3x squared plus 12x minus 36 equal to 0. Dividing every term by 3, we get x squared plus 4x minus 12 equals to 0. This is a quadratic, and we factor it as x plus 6 multiplied by x minus 2 equal to 0. This has two solutions at x equals minus 6 and x equals 2. The next example, we look at the product that involves both x and 1 over x. We have x plus 1 over x bracket multiplied by x squared minus 2. This is a product of two differentiable functions, so we use the product rule. Let f of x equals x plus 1 over x and g of x equals x squared minus 2. We first find the derivatives of f and g. For f of x, the derivative of x is 1, and the derivative of 1 over x is negative 1 over x squared by the power rule. So we have 1 over x equals x to the power of negative 1. We, we take the negative 1 as a coefficient and subtract 1 from negative 1, so it becomes negative 2. Then the derivative of 1 over x is negative 1 over x squared. So f prime of x equals 1 minus 1 over x. And for g of x, the derivative of x squared is 2x, and the derivative of negative 2 is 0. So g prime of x equals 2x. Now we apply the product rule. So y prime equals f prime of x times g of x plus f of x times g prime of x. Substituting, we get y prime equals 1 minus 1 over x squared, all multiplied by x squared minus 2 plus x plus 1 over x multiplied by 2x. At this point, you can simplify the expression if needed by expanding each bracket. The important idea is that we have correctly applied the product rule. Derivative of the first factor times the second plus the first factor times derivative of the second. Our last example is a quotient. We have y equals 3x squared plus 1 divided by x squared minus 4. Here we use the quotient rule because we have one function divided by another. Let f of x equals 3x squared plus 1 and g of x equals x squared minus 4. Then f prime of x equals 6x and g prime of x equals 2x. The quotient rule states that y prime equals f prime of x times g of x minus f of x times g prime of x, all divided by g of x squared. Substituting f prime, g, and g prime into the formula, we get y prime equals 6x multiplied by x squared minus 4 minus 3x squared plus 1 multiplied by 2x, all divided by x squared minus 4 squared. So we can simplify the numerator step by step and get 6x multiplied by x squared minus 4 equals 6x cubed minus 24x. And the second term, 3x squared plus 1 multiplied by 2x equals 6x cubed plus 2x. So the numerator becomes 6x cubed minus 24x minus 6x cubed minus 2x, or negative 26x. Therefore, y prime equals negative 26x over x squared minus 4 all squared. This example shows clearly how the quotient rule combines the derivatives of the numerator and denominator. We just follow the formula carefully, then simplify the result. In all these examples, notice the pattern. We identify the structure of the function, whether it is a sum, product, quotient, or a composition of simpler terms. Then we choose the appropriate rule and apply it step by step. With practice, these calculations become much faster and more natural. Now it's your turn. We have 3 exercises. Pause the video and try to solve them yourself and put your answers in the comments. The first, f of x equals bracket 2x cubed minus 3 close bracket multiplied by 2x squared minus 5 bracket and multiplied by x cubed minus 4x plus 1. And you are asked to find f prime of 0. Here we should apply the product rule step by step and then substitute x equals 0. The second example is f of x equals x squared minus x minus 2 all divided by x squared plus x minus 2. And you need to find f prime of 2 and f prime of negative 2. This is a direct application of the quotient rule followed by substitution. The third example, we have a piecewise function. F of x equals ax plus b for x is greater than or equal to 1, and f of x equals x squared minus 3 for x less than 1, with the condition that f is differentiable at x equals 1. You should use continuity at x equals 1 to relate a and b, and then use equality of left and right derivatives to determine their exact values. Before we finish, let's briefly look at the solutions of 3 exercises from the differentiation lesson. First, the piecewise function f of x. First, the piecewise function, which is given to be continuous at x equals 2. Matching the left and right values at x equal 2 gives. Let's briefly look at the solutions of the three exercises from the differentiation lesson. Let's summarize what we have done in this lesson. We started from the limit definition of the derivative and used it to motivate four practical rules: the derivative of a constant and a linear function, the derivative of x to the power of n, the sum and difference rules, the product rule, and the quotient rule. We applied these rules to polynomials, products and quotients, and to piecewise functions. With these rules, you can now differentiate a wide variety of functions quickly and accurately, which will be very important in all later topics in calculus. Thank you for watching and see you in the next lesson.